So here is the link to sign in. Okay, when it asks you for your ID number, please make sure you use your permanent ID number. Your long ID number, it's the 8-digit one, starts with your year of enrollment. Okay, it's also on your ID card. All right, so again, if you came in a little late, here is the link to get signed in. Make sure you use your long ID number. So it looks like we have Brianne Romero, Andrea Mora, Alexa, Eliana, Heidi, Jayla, and Janet. So it looks like we're still waiting on about 3 more of you to get signed in. All right. Well, today's goal is to review for the test tomorrow. So, for this week. So if you're in my class, you have it tomorrow, but depending on when you have chemistry class, you'll have it sometime this week. So what I want you to do right now is take out a piece of paper and a pencil, and we're going to focus on what to review for the test tomorrow. So I'll give you a minute. Paper, pencil, make sure that's handy. All right, so a few more seconds before we get started. All right. So let me share my screen with you. First thing we're going to take a look at are some of the properties of water. So your test this week is going to cover water and its properties, solutions, and acids and bases. If you have any questions, you're more than welcome to ask those questions at the end. Also, please make sure you have your camera on during tutoring so we can verify that you are here. So let's go ahead and jump over here real quick. So can you guys see these pictures of water molecules? Give me a thumbs up. Okay, good. So let's take a look at this first picture. This picture has a water molecule. We have oxygen bonded to 2 hydrogen molecules. Well, oxygen is the more electronegative atom, meaning oxygen has a higher attraction to electrons than hydrogen is. So oxygen will have a partial negative charge. Hydrogen will have a partial positive charge. Okay. Well, what this does is this causes water to be polar, meaning we have one side is partially negative, one side is partially positive, so this creates a polar molecule. Well, as a polar molecule, the water will actually bond to other water molecules through what we call hydrogen bonds. So because hydrogen is partially positive and oxygen is partially negative, then the hydrogen of one molecule will be slightly attracted to the oxygen of another molecule, and this is what forms the hydrogen bond. So a hydrogen bond is a bond of attraction between a slightly positive hydrogen atom and a slightly negative oxygen atom on a different water molecule. So that's hydrogen bonding. Now together, these properties, the polar nature of water, the hydrogen bonding, they go to make water what we call the universal solvent, where it can dissolve many substances, many solutes. One of the other features that this results in a water molecule is called capillary action. So give me a second, I didn't have this pulled up. Okay, so called the capillary effect or capillary action. We see this in plants, but here's a picture that shows if you stick like a paper towel or a piece of paper in water, the water will naturally move up the column. So this is called capillary action, where the water molecules travel up against gravitational forces, and due to the cohesive forces, those forces of attraction between water molecules, they will pull other water molecules up the tube. So if we look at it in plants, okay, so here's an example in plants. In the root system, water is absorbed through the roots and it gets pulled up the stem. So water is pulled up and evaporates out the leaves. And so you actually have water that gets pulled all the way up through the plant through capillary action. Okay. All right, so real quick, I'll pause here for a second. So remember, you guys are taking notes. So you could sketch these pictures. You can take notes on what I'm talking about. So far, what I'm doing is going over keywords. So some of the keywords I've discussed are capillary action. Let's see, polar molecule. So water is a polar molecule. Hydrogen bonding. Okay, so these are some of the key terms that you want to know for your test. Another word that you want to know is surface tension. Okay, so let's see if I can get a good, all right, here's a few pictures that'll help us. So with surface tension, okay, if you have something on the surface of the water, gravity is pulling it down, and so if it's more dense than water, it should sink. However, if the surface tension is strong enough compared to the weight of the object, you can actually get things to float if they don't break the surface tension. So what causes surface tension? So remember we talked about water molecules having hydrogen bonds. So each of these circles represents hydrogen water molecules. Well, and the arrows represent hydrogen bonds. So these water molecules can attract water molecules all around it. Okay, top, bottom, left, right, sideways, diagonal. These water molecules can attract water molecules in all directions. So their hydrogen bonds and those bonds between water molecules can be oriented in any direction. Okay. However, at the very top of the water molecule, those water molecules can only be attracted to each other sideways, or they can have force of attraction below the water molecule. So this one actually does a better job showing that. So you can see here that at the surface of the liquid, all of those forces of attraction are either directed sideways, down, or diagonal and down, but there's nothing attracted above it because there's no water molecules above it. So because we have a greater concentration of those forces of attraction, we find that the surface tension is a lot stronger, we find that surface tension at the surface because of all those forces of attraction. If we look at a water droplet, it also helps explain why water droplets maintain that rounded shape because of the same reason. All the particles at the surface of the water have forces directed sideways or in towards the center of the circle. And so that's why we get the water rounded in this certain shape. And if you actually had this up in space, it would be like a perfect sphere. Whereas on Earth, when the water droplet is falling, it forms that little tear shape because of the air resistance. But again, that's because of the hydrogen bonding involved in the water molecules. Well, application, where do we see this, or where do we see the effects of this? We see one of these little walking spiders. So in this walking spider, you see that the spider is actually walking on water. Normally, the spider would sink, okay? But because of the way it spreads itself out, because it has a small enough mass, and because it has what's called hydrophobic hairs that prevent it from going in, it's kind of like sitting on little floaties. So because of that, the surface tension in the water is strong enough to keep these water spiders above the surface so they can quickly run across the surface of the water. That also explains why you can get a paperclip to float at the top of water, even though a paperclip is probably more dense than the water itself. If you lower it carefully enough, and you could try this at home. If you're in my class, we actually did this on one of the first days back. But you could get the water or the paperclip to float on the surface of the water as long as you lay it flat and gently. That also, surface tension also explains why it hurts a lot when you do a belly flop. All right, so I've covered a lot of terms with water so far, so I'm going to pause it here for a second, give you guys a chance to get caught up, and let me know if you have any questions. So again, if you have questions, go ahead and put them in the chat. Okay, last call for questions before we move on. So again, some of the words that we've reviewed that you'll want to know for the test would be polar. So what does it mean that a molecule is polar versus nonpolar? Hydrogen bonding, okay, surface tension, capillary action. Okay, we ready to move on? No questions so far. If you do have a question, just feel free to put a message in the chat. That'll be my cue to stop and take a break to explain something or give you guys a chance to get caught up. Also, I am recording this. I have it spotlighted on my video, so it won't be recording any of your faces. It's just recording me. And so I will probably post this on Google Classroom tonight. So you guys have the benefit of actually being here. You guys are making the study sheet, and you get the extra credit for being here. So you get quite a bit. But I'm also posting it because a lot of people are unable to attend tutoring because of sports. So this will allow them to still watch the video without actually getting the extra credit for being here. So just keep that in mind, that if I am going too fast on anything, this will be recorded, and as long as it records correctly, I will post it tonight on Classroom, and then your teachers will probably post it as well. Or I know one or two of you are not in my class, so if you email me, eric.york at Capillary. I'll just put it in the chat. If you email me, then I can send it to you directly as well. Okay, so there's my email, eric.york at Capillary.k12.ca.us. Okay, so moving on to the next one. Okay, so again, just a recap of some of those properties of water. We have water is polar, Water is an excellent solvent because of its polarity, because it's able to attract many types of solutes. It has a high heat capacity because of those strong bonds between the water molecules, and therefore high heat of vaporization. Cohesive and adhesive properties. Remember, cohesive is when the water molecules stick to each other, so they pull on each other. So water molecules are cohesive. And then adhesive, think of like adhesive tape. You could use adhesive tape to stick two different materials to each other. So adhesive properties would be water molecules sticking to other types of molecules. Also, we find that water is less dense as a solid. So most things, when they become a solid, they become more dense and sink. However, water is unique in that when it becomes a solid, it actually becomes less dense and floats. And that's actually really important to life on Earth, because when a pond or lake freezes over, we only get ice at the very surface, which allows for fish and other life forms to still live underneath it. However, if ice were to sink when it became a solid, then the entire lake would eventually freeze over, killing everything in it, and that would really cut down on a lot of the life that we have in lakes and ponds. So it is a very important property that ice floats. All right, now transitioning to solutes and solvents. Okay, here's a picture that I like. So remember, solute is the thing that gets dissolved. The solvent is the thing that does the dissolving, and the solution is the mixture of the solute and the solvent. So in this case, we have some blue powder here, probably something with cobalt in it. So we have this blue powder. It's mixed with water. So the powder is a solute. The water is the solvent. So the powder will get dissolved in the water. And so again, that goes back to our definition of solute versus solvent. Now, there's some other terms that we need to understand with solute and solvent is concentrated versus dilute. So in a concentrated solution, okay, you can see the concentrated solution is darker because so these blue spheres, these blue circles are the solute, and the purple ones are the solvent. Okay, so in the concentrated one, we see a lot larger ratio of blue to I don't know if it's red or purple, whatever. So we'll call it red. So we see a larger ratio of blue solute to red solvent. So we call that a concentrated solution. So remember, solutions exist as ratios. So let me do this. So the term for concentration looks like this. So the brackets, it's a ratio of solute. Can you guys see me writing on it, by the way? Give me a thumbs up. Good. Solute divided by the solvent. So all of our equations that we have looked at in this class for concentration involve this ratio. Okay, it's a ratio of solute to solvent. So if you have a high concentration, a concentrated solution, that means you have a large amount of solute per solvent. So we see that in this circle here on the left because there's a high ratio of blue solute particles to red solvent particles. Okay, in a dilute solution, you have a lot fewer of those ratios. So this ratio is lower. So the ratio of solute to solvent is very low in a dilute solution. So here we have 1, 2, 3, 4, 5, 6 blue particles and a lot more of the red particles. So this is a very dilute solution. Okay, let's see. Also, just keep in mind that when we're doing mass, remember most of our equations will call for the mass or volume of the solution itself, not the solvent. So you need to remember, make sure you look at the equation and know what the equation calls for. But most of the time, it's going to call for the volume of the solution or sometimes the mass of the solution, not the solvent. So keep in mind that the mass of the solution is the combined mass of the solvent and the solute. So in this case, the mass of the solution is 110 grams, or if it gave these measurements in milliliters, let's say 100 milliliters plus 10 milliliters would be 110 milliliters. So keep that in mind. Okay. One thing I want to make sure we do is understand how to do conversions with the metric system, because you'll have one or two of these on here. So give me a second. All right. So again, thumbs up if you can see me writing on the board right now. Okay, perfect. Okay, so let's just say we had 2,000 milliliters. My question is, how would we convert that into liters? Because sometimes on the question, it'll give us milliliters and we have to convert it to liters. Sometimes it'll give us liters and we have to convert it to milliliters, so we have to be able to do that. So, for example, on a molarity question, the equation for molarity is moles of solute per liter of solution. So again, that's moles of solute per liter of solution. So again, there's that ratio I was telling you about. So concentration is a ratio of solute to solution. So the first equation we looked at is moles of solute per liter of solution. Well, if the problem gave us 2,000 milliliters, well, we need to be able to convert that into liters. So we could use King Henry, we could use dimensional analysis, there's different ways. So using King Henry as our method, we have King Henry died by drinking chocolate milk. And again, if you have a different method, just use a method you're comfortable with. This is one of the ones I go over in class. So milliliters is right here. Okay, that's milli. And we would need to convert it to liters, L, which is our base unit. So we're going to move the decimal 1, 2, 3 spots to the left. Yes, that is correct. I just saw some people put in some answers. Yep, moving the decimal. All right, sorry, but the direction's wrong. So make sure you're moving the decimal in the correct spot. So we're moving the decimal to the left 3 times. So here's the original decimal. We need to move it 1, 2, 3 spots to the left. So 2,000 milliliters would be equal to 2 liters. So if this was a molarity problem and we had to calculate liters, if we had to use liters, we'd move the decimal 3 spots to the left to get it in milliliter, or sorry, to go from milliliters to liters. Well, let's say instead we had a problem where it gives us 15 liters, and let's say this is a percent problem where the percent equation is equal to the volume, and this could also be mass of volume in milliliters of the solute divided by the volume measured in milliliters of the solution. So again, we have solute on top and then the solution on bottom. Whoops, sorry, this is supposed to be solute on top, solution on bottom. And again, I apologize, I don't have my writing pad like I normally do. And we multiply that by 100. So that's the equation for percent. Volume of the solute divided by volume of the solution times 100. And we could also do this in terms of mass as well. So instead of milliliters, we could use grams here. So we have this question, but notice the equation calls for milliliters, but we have liters. So we need to convert this to milliliters. So I just showed you how to do it with King Henry. So I'll do that real quickly for you as well. But then I'm going to show you dimensional analysis. King Henry died by drinking chocolate milk. So we're going to do just the opposite. We're going to move the decimal 1, 2, 3 spots to the right. So 15 liters becomes 15,000 milliliters. So there's the decimal. and we move the decimal 3 spots to the right, and each time we move it, we're filling in a 0. Okay, so, or you could also do it this way. 15 liters times 1 liter is 1,000 milliliters. So 15 times 1,000 is just equal to 15,000, which is what we already got. So either way, both of those will allow you to convert liters to milliliters. So that's one thing you need to be able to do on the test is your conversion from milliliters to liters. So, or since you have your cheat sheet, just do an example problem. 15 liters, show how to convert that to milliliters. Or like we did on the last one, was it 2,500 or whatever number we use, 2,500 or 2,000, I think. 2,000 milliliters, convert that into liters. Okay. All right. Again, any questions before we move on from these metric conversions? Okay. No problem. Just again, I have somebody who messaged me. If you need to, just check this video tonight to see the part that you missed when you do have to leave. Okay, the other equation we haven't looked at is ppm, but ppm is very similar to the percent one we just did. So ppm is equal to, again, we could do mass or volume. So it's the mass, that's an A right there, mass of solute in grams divided by the mass of the solution also in grams, but again, this could be milliliters. And instead of multiplying it by 100, we're going to multiply it by 1 million. Well, the scientific notation, the exponent form of 1 million is just 10 to the 6th power. So just know 10 to the 6th power is 1 million. So you take your mass of solute, divide it by the mass of solution, multiply it by 1 million, and that will give you your concentration in ppm. So here's some application. And again, if you're in my class, we talked about this. Water quality testers, they go out and test it. And they say that, so according to I think it's the FDA, you could have 0.01 ppm of arsenic. Okay, so as long as your concentration is 0.01 ppm arsenic or lower, the water is safe to drink. However, if the concentration reaches that quantity, it becomes unsafe to drink. Okay, so I'm going to give you guys a second to actually try this problem, and we'll see if anybody gets it. So let's say we have 30 liters of water. Okay, 30 liters of water. And we know that a concentration of 0.001 ppm is the limit for being safe. So if we have 30 liters of water, what is the amount of arsenic in grams? What's the total amount of arsenic in grams that you could have in there before it becomes unsafe? So basically using this concentration and using this volume, how many grams of arsenic can be in that 30 liters of water before it reaches that point of being unsafe? Okay, so what you do is you take this number, you plug it in for ppm, you take 30 liters, you have to convert it to grams because it's an aqueous solution. So remember 30 liters, you have to first convert that into milliliters because 1 liter is 1,000 milliliters. So using King Henry, like I just showed you, and then once you have milliliters, remember that 1 milliliter is equal to 1 gram. So here, let me do it this way. So we have to convert your milliliters into grams because 1 ml equals 1 gram of aqueous solution because the density of an aqueous solution is 1 gram per milliliter. I had somebody join just now. Okay, here's a link to get signed in, so make sure you sign in. Okay, so again, I'm going to give you guys about a minute to 2 minutes to try to do this. All right, good. When you have an answer, go and put it in the chat, and we'll take a look at it. Okay, just remember 30 liters is 30,000 grams. So 30 liters is 30,000 milliliters.
I tried my combo. What are we solving for again?
Solving for the mass of solute. So I showed you the total volume of, sorry, I put water, but that's supposed to be of solution. So this is 30 liters of water solution. So 30 liters of water solution. And the concentration is 0.01 ppm. So how many grams of arsenic would be in that solution? Okay, also be careful where you plug it in. So remember, you're plugging in the concentration here. You know 30 liters is 30,000 grams. So now your unknown is the mass of the solute. All right, so I'm getting a few different answers. I'm getting close answers, but not quite the correct answer yet. So the correct answer is actually 0.003. So 0.003. So I'll put the answer up here, and then I'll show how to get that in just a minute. Okay, so there's the correct answer right there circled, 0.003 grams. So again, I'll help you plug it in. So this is 0.01 ppm is equal to, and so we're trying to solve for mass of solute. I'm just going to call that X divided by, and then the mass of the solution is 30 liters, but that would be 30,000 milliliters, which is 30,000 grams. And we're going to multiply that by 1 million. Okay, now at this point, it's just algebra. And what I recommend is cancel out some of those zeros. So I know those 3 zeros are gone, that 0 is gone, So this basically simplifies to, so 0.01 equals, so now this is 100 times x divided by 3. And now I just have to solve for x. So multiply both sides by 3. So this becomes 0.03 equals 100x. Divide both sides by 100. And again, you can use a calculator. There will be a calculator option on the test. So when in doubt, just use a calculator. So 0.03 divided by 100 is 0.0. Oh, I put the wrong number of zeros up here. 0.0003. Be careful with that on the test. Let me just double check it one more time since I had the wrong number of zeros up there. Yeah, correct. There should be 3 zeros in there. So 0.0003 grams. Okay, any questions? Okay, so again, you'll have one of each of those types of questions on the test. You'll have a molarity, and actually you'll have 2 molarity questions. You'll have a percent question and a parts per million question. For a question like this, the way the question might work is, so since we just found that the 0.003 grams would be would be that threshold, the question might say if your water sample contained 0.0002 grams of arsenic, okay, would it be safe? Okay, so the question might say if that's how much arsenic was there, is that safe? So then you can use this number, determine the concentration, compare it to that concentration, and if it's lower than the safe concentration or the limit, then it's safe. If it is higher than this limit, it would be unsafe to drink. So that's how the question will look on the test. So make sure you guys understand how to what this question is saying. So again, if this right here is the dangerous limit, and I give you the volume of solution and the mass of solute, you can determine the concentration in ppm and then compare the calculated value to this value. If it's larger than that value, it's unsafe because it's at too high of a concentration. If your answer is less than that number, it's okay to drink. It's in the safe range. All right, and I'll show you one more because molarity is important, so you'll have 2 of these. So let's say for molarity, I give you the concentration in molarity is 4 molar, and I tell you that you have 3 liters of solution. Well, how many moles do you have? So you need to remember the difference between moles and molarity. Molarity is measured in moles per liter, so I could call this 4 moles. So that's 4 moles. Or I could call it 4 moles per liter. Either one of those units, or sorry, not 4 moles. I am really confusing you. 4 molar. Okay, so I really messed that one up. So 4 capital M is 4 molar or 4 moles per liter. So this is supposed to be MOLAR. It is not 4 moles. So I need to be careful there. So when you see the 4 followed by a capital M or a number followed by a capital M, that capital M stands for molar, which is the same as saying moles per liter, and it is not the same as saying moles. So now we're trying to find the number of moles. So here's my question mark. So set up our equation. Molarity, again, is equal to moles per liter. Okay, plug in our numbers. Molarity is 4. Moles is unknown. Liters is 3. So what would be our number of moles? Go ahead and put it in the chat. Good. $12 moles. Okay. So any questions on how we did this? All right, now for the last part, let's go ahead and jump over to pH. So let me pull up the pH practice here. So for acids and bases, remember some of the characteristics of acids and bases. So acids have a high pH. Actually, let me see if I can pull this up real quick. And I just lied. Acids have a low pH. Low pH. Sorry, I can't multitask. Okay, so let's look at this website real quick. So some differences between acids and bases. So acids taste sour, bases taste bitter, they feel slippery, they dissolve fats and oil. Acids will react with some metals to give off hydrogen gas, and acids conduct electricity in solution. Okay, the pH of a solution is a measure of the hydrogen ion concentration in a solution. So our pH scale ranges from 0 to 14. So low pH values, so way down here on the left side, those are strong acids with low pHs. And then higher pHs over here, like household cleaner, like bleach or Drano, those involve basic solutions with a high pH. And then things in the 7 range are neutral, such as water or milk. Okay, so there's some different definitions. You don't need to know the difference between these on the test, but they talk about one of the important ones that you actually do need to know is that an acid, according to Arrhenius concept, is a hydrogen ion donor or producer. It makes hydrogen ions, whereas bases have a large concentration of OH minus. So that one you actually do need to know for the test. So acids will produce a lot of H pluses, hydrogen ions, whereas bases will produce hydroxide ions, OH minus. Okay. And so if we look over here, something with a high pH, a basic solution, will have a high concentration of OH minus, whereas acids down here with low pHs will have a high concentration of H plus ions. Okay. Again, an acid is a proton donor, and a proton is just another word for H plus. So that's a proton. So acids will donate or give off a proton, whereas bases will accept or take in a proton. Okay, let's see. So we talked about pH value, so pH ranges are low. So let's go back and look at the pH scale. So let me pull up a good picture for the pH scale. Sorry, give me a second to look for one in particular. I think that one's good quality. Let's see. All right, we can just look at one of these up here. All right, so looking at this, pH ranges from 0 to 14. So we can see like a battery over here, battery acid, pH of 0, very acidic. Stomach acid is really acidic. Then we have lemon juice. Sodas are down here at a 3, pH of 3. Tomatoes are at a 4, coffee at a 5. Milk is about a 6. Water is neutral. Blood has a pH of 8. Egg whites, pH of 9. Stomach tablets, so like the if you ever take Tums or something, ammonia solution, pH of 11. Soap, pH of 12. Bleach, pH of 13. Drain cleaner, pH of 14. So we have acidic solutions to the left, low pHs, alkaline solutions to the right. So make sure we understand that over here on the acid side, okay, so we have low pH, which corresponds to a high concentration of H plus ions, okay, and that corresponds to a low concentration of OH minus. Remember, OH minus is hydroxide, H plus is hydrogen ion. So those are acids. So the lower the pH, the higher the H plus concentration, the lower the OH minus concentration, and then bases are just the opposite. Okay, so a base has a high pH, okay, which means it has a low concentration of H plus, and therefore has a high concentration of OH minus. Well, one of the equations we looked at was pH plus POH equals 14. So on our pH scale, so again, this is our pH scale, it ranges from 0 to 14. Well, according to this equation, a pH of 0 would correspond to a POH of 14. And then a pH of 14 would correspond to a POH of 0, with our neutral 7 being right in the middle. Okay, so what that means, if I told you that the pH of something is 11, okay, so you should be able to use this information to tell me about what that means. So if somebody has a pH of 11, that means it's going to be somewhere in this area right here. So that means it's a base. It has a high pH, low concentration of hydrogen ions, high concentration of H minus, and a low POH. So if it has a high pH, that means it has a low POH. Okay, and same thing. If I said somebody has a pH of 3, okay, that would be in this area right here. So pH of 3 means it's an acid. It has a low pH, high concentration of hydrogen ions, low concentration of OH minus ions, and since it has a low pH, it would have a high POH. Okay, so again, that's a review of the pH scale. Also, it's important to remember that it's a log-based scale. So a pH of 6 versus a pH of 7, a pH of 6 is actually 10 times more acidic than 7. So coffee is 10 times more acidic than milk. So that means it is 100 times more acidic than water. Tomato juice is 10 times more acidic than coffee, 100 times more acidic than milk, and 1,000 times more acidic than water. Okay, and then I'll do one more, soda. So soda is 10 times more acidic than tomato. It is 100 times more acidic than coffee. It is 1,000 times more acidic than milk, and 10,000 times more acidic than water. Okay, so that shows you how the pH scale operates. Now, we already talked about this equation right here, where the sum of the pHs adds up to 14. The pH and the pH adds up to 14. But now let's look at the other equations. Okay, and before I go on, let me know if you have any questions. If anybody has a question, let me know. Because now we're going to take a look at this practice worksheet. All right, so given the concentration, or given any one of these, if we know that H plus concentration, we can calculate the pH. If we know the pH, we can calculate the pOH. And then if we know the pOH, we can calculate the concentration of OH minus. So basically, if we know any one of these four, we can calculate the other three. We just have to remember which equation it is to use it. So step one here, since we're given the H plus concentration, I'm going to show you how to calculate all three of these, not just the pH. In this problem, it says calculate the pH, but we need to know how to calculate all three of the others. So I'm going to do two examples of this. So if it gives us the H plus here, all we have to do is look at the exponent. Assuming this is a 1 out front, then the exponent itself is the pH, because the equation for H plus, so concentration of H plus, is equal to 1 times 10 to the negative pH. So the exponent itself is the pH. So the pH here is equal to 12. So this is a basic solution. Okay. Now, the second one is if I know the pH, I can calculate the pOH, because again, the next equation I need to know is that the pH plus the pOH equals 14. Well, I already know that the pH is 12, so I put a 12 here. 12 plus my pOH equals 14. Well, now I just need to solve for my pOH using algebra. Subtract 12 from both sides. Okay, so I get that my pOH is equal to 2. So remember, low pOH corresponds to a high pH, corresponds to a basic solution. Well, the third thing I can now do, so number 3, is convert that to hydrogen ion concentration. So again, it follows the same type of equation where the concentration of OH minus is equal to 1 times 10 to the negative pOH. So all I need to do is take that number and write it here. So I get the concentration of OH minus equal to 1 times 10 to the negative 2, and that would be measured in molars. So 1 times 10 to the negative 2 molar. So I just showed you how, given one of these, we can convert it to pH, we can convert it to pOH, and we can convert it to OH minus. Okay. On the test, I don't think you'll have one this this difficult, but just remember, if you have to move the decimal 2 spots, this would be 1 times 10 to the negative 2. So then the pH of that would be 2. So if the pH is 2, so again, here's the pH, that means that the pOH would have to be 12. So kind of the opposite of this. So then the concentration of OH minus, so again, right now I'm doing number 7. The concentration of OH minus would be equal to 1 times 10 to the negative 12. So those are your answers for number 7. All right. Any questions? I'm done covering everything for the test. So I've covered most questions on the test, and actually let me go through real quick to see if there's anything that I missed off the top of my head. Saturated versus unsaturated. Saturated is when you have as much of the solute dissolved as possible. Unsaturated is when you can dissolve more. So like if you make Kool-Aid mix and you just put a little bit of Kool-Aid in, you have an unsaturated solution because it can dissolve more. And then if you fill it up where basically right to the point where it's about to, you'll start to see Kool-Aid fall to the bottom, then that's the saturated point where you can't dissolve anymore. So that's saturated versus unsaturated. Okay, we talked about the units for molarity. Somebody asked about the answer sheet to this. Give me a second and I will pull up the answer sheet to this one. Okay, here's a question for you guys to think about while I look for that. So if I'm trying to make a solution and I add too much water to the solution, so I'm trying to make a specific concentration of solution and I add too much water to it, does that make it more concentrated or less concentrated than my target calculation? So again, try that out. I'm going to stop sharing my screen for a second. So your question is, if I'm trying to make a solution and I accidentally add too much water to the solution, so compared to my target concentration, would my actual concentration be too concentrated or too dilute? Okay, so I just realized I don't have a key to that. So if I have time tonight, I will make a key for this. But if you have any questions on any of them, I can go over them in a couple of minutes. And yes, the correct answer was too dilute. If I added too much water to it, that means I lowered the ratio of solute to solvent, so it is too dilute. Okay, at this point, you are free to go. But since I don't have a key made up for this practice, if you have a question on any of them, I can help you out. Also on that worksheet on the back side, remember that when it says H3O plus, that's the same as saying the H plus concentration. Okay, so again, you are free to go right now, unless you have a question